Okay, so if T2 is just the zero operator, then we stop if T2 is not the zero operator. Then all we're going to do is repeat the arguments we basically had before. So if this is true, then plus or minus the norm of T2, which I'll call lambda 2, one of these, because T2 is compact self-adjoint. Well, I had it before, so I won't write it again. This is an eigenvalue, one of these, of T2 taking M1 perp, M1 perp. Yeah, let's say, G2 is an M1 perp. Just remind you what that is. It's the span G1 perp. So let's say this is a normalized eigenvector of T2. And that obviously means this is an normalized eigenvector of T, because T2 is T, just restricted to M1 perp, right? So something to note, well, G1, G2 is, they're certainly orthogonal. G1 is in the orthogonal complement of the span of G1. So G2 and G1 are orthogonal, they're normal. So this is an orthonormal set of eigenvectors of T. All right, so yeah, so let's just repeat. I'll just do one more and then write down what happens if we just keep going and going. So let's say M2 is the span of G1, G2. Right, so certainly M2 is a invariant subspace of T, right? Because these both are eigenvectors, so with corresponding eigenvalues lambda 1, lambda 2. So if X is in the span, so X is going to be alpha 1 G1 plus alpha 2 G2. Just repeating what we had before. Tx is going to be alpha Tg1 plus alpha 2, sorry, alpha 1 Tg2. And this is just going to be alpha 1 lambda 1 G1 alpha 2 lambda 2 G2. Right. So because T is self-adjoint, so T takes M2, or Tm2 is a subset of M2. And because T is self-adjoint, as we had before, this means T M2 perp is a subset of M2 perp. Okay. So set T3 to be T restricted to M to perp. Right, so if the norm of T3 on M2 perp is 0, we stop. If not, just continue, and I'll just do one more to get G3. One of these is an eigenvalue. So yeah, like we said before, this is the restriction of a compact operator to a subspace. So this is compact. And because T is self-adjoint, T3 is self-adjoint. This is an eigenvector, eigenvalue of T3. So pick a normalized corresponding eigenvector rather, G3 in M2 perp. So that, well, this is orthogonal complement to the span of G1 and G2. So again, just like before, this is an orthonormal set of eigenvectors. With corresponding eigenvalues. Well, it's a little annoying to write it like this, so I'll write it like this here. Lambda j equals 1 to 3. And I really should start writing that because it's kind of silly. Okay, so we just keep continuing. And we just keep going and going and going. Right, so basically we just continue, assuming that we never stop. So we continue to get, yeah, so we continue on to get, let's say we get an orthonormal set, Gj, j equals 1 to n of T. With corresponding eigenvalues lambda j equals 1 to n. Where, and I'll say what happens if we do stop, but let's assume that we just continue and we don't stop. Right? So we get lambda j and modulus, or absolute value rather, is the norm of Tj, which goes from mj minus 1 perp. Make sure that's right. Yeah. To mj minus 1 perp. And this is not going to be 0 by assumption. And Tj is just T restricted to M, J minus 1 perp, with M, J minus 1 just being the span of the GJs. L yeah. Okay. Right. So yeah, so we have two cases. So yeah, so I'll just quickly go over this one last time, kind of what to do. Sorry. So this is a orthonormal set of eigenvalues of T, eigenvectors rather. All right, so just to remind you, I won't go through this detail. So T M, let's do Mn is a subset of Tmn. Sorry, Tmn is a subset of Mn because Mn is a span of n eigenvectors. So because T is compact self-adjoint, that implies T Mn perp subset of Mn perp so let's say Tn plus 1 is just T restricted to Mn perp takes Mn perp to Mn perp. It's over a bit. So yeah, sorry, if this is 0, well, otherwise just do exactly what I've been doing. Just keep going. I'm not going to keep repeating it. So ultimately, we have two cases. First case is, well, we stop at some point, okay? We know that T is not 0. So we do not stop at the very beginning. We at least have one genuine eigenvector, okay? So in other words, as I mentioned that we set T1 basically to be T. T2 is T restricted to the span of the first eigenvector G1 and then keep going. But in general, the first case is we stop somewhere, or more precisely, there exists a smallest natural number m where Tm is 0, and not so much natural number, but m is bigger or equal to 2. Okay. And just again, remind you of why this is true. T1 is T is not equal to 0. Okay. So m can't be 0. T, I guess I'll just leave it at that. T m equals 0. Okay. If so, then what do we have? Okay, so let's let X be an H. And so we're going to employ a little trick, and we'll use this, many times in the rest of the proof. It's a very clever idea. Let's say y is going to be x. So let's say y is basically the projection of x onto the orthogonal complement of little m minus 1. So that is just going to be x minus this sum here, x gj gj. This one here is the orthogonal projection onto little m minus 1, and this is the orthogonal projection onto the orthogonal complement. Okay. Or if you want, you can just check that this is going to be check directly. This is in yeah, so just to remind you, actually, this is going to be t restricted to m minus 1 perp, which goes from m minus 1 perp to m minus 1 perp. Okay. Yeah, so you can check directly if you want, because this, remember, this is just a span of the GJs. J equals 1 to m minus 1. This is going to be in the orthogonal complement. All right, so what does that mean? Well, apply t, we get 0. Okay. T restricted to this is 0. Y is in this, so ty equals 0. Zero is ty is going to be tx minus, just use linearity. Oops. Sum j equals 1 to n, x gj, t gj. Well, this is just going to be, because gj is an eigenvector, corresponding eigenvalue lambda j. So it's going to be the sum here. So what does this mean? This means that tx, well, just, whoops, that. It's going to be tx minus this. So this means that tx, just add this to both sides here. Tx is going to be this sum here. All right. All right, and in this case, we're almost done, not quite. But let's just do the other case, which is this is not 0 for any natural number m. We just keep repeating this process. Okay, so what happens in this case? First, since E lambda, remember this is the eigenspace of t for any eigenvalue lambda. We proved that this is finite dimensional. So in other words, what does that mean? That means that there are no infinite repeats in the collection of these eigenvalues lambda j equals 1 to infinity. Right. Why is that? Assume there is a subsequence. Let's say lambda is lambda n1. So let's assume there's there's an infinite repeat. So we have a subsequence n1, n2, where lambda n1 equals lambda n2, et cetera, et cetera. Okay. Well, in that case, what does this mean? Well, this means that GNJ is an orthonormal set in E lambda. Right? The GNJs are an orthonormal set by construction. Well, that violates E lambda being infinite dimensional. I mean, it violates E lambda being finite dimensional. So this is not finite dimensional. Okay, right. So what does this tell me? This tells me that we don't have we don't have any infinite repeats. Okay. Right. So we certainly do have genuinely an infinite set. That's kind of what's important. Okay. And remember, we called the set of all eigenvalues of t sigma pt. And I'll explain in a moment. This is actually all the eigenvalues. You can, yeah. But anyway, for now, yeah. So for now, this is just an infinite set of eigenvalues. Okay, well, T is compact. So we proved that if we have infinitely because there's nothing repeated infinitely, we have an infinite number of eigenvalues, and we proved that if that's the case for a compact operator, then you know, the eigenvalues have to converge to 0. There can only be countably infinitely many eigenvalues, and the eigenvalues have to converge to 0. Okay, so we get part of what we want to prove, that this is 0. Okay, which is actually very important for the for us when we finish finishing the proof. So, all right, so basically do the same thing as we did before. let's say yn is going to be, again, the orthogonal projection of some arbitrary element in my Hilbert space in Mn perpendicular, the orthogonal complement of Mn. So j equals 1 to n. X gj, gj. So this is going to be Mn perp, right? Right. Again, just this is pretty trivial. So not going to say why again. So what does this tell me? This tells me that x squared is going to be x minus yn plus yn. Well, this is an Mn because it's just, this is literally some x gj inner product gj, and you know, certainly that's in the span of the gj's, not much to that. This is an Mn orthogonal complement. So this is going to be equal to x minus yn norm squared, yn squared. In particular, it's bigger or equal to the norm of yn squared. Okay, right. So what does this tell me? This tells me that Tyn. So what I want to show is that Tyn converges to 0 as n goes to 0. Why? Sorry, as n goes to infinity. Well, Tyn is going to be Tx minus this sum here. Just using the fact that, again, the GJs are an orthonormal, well, the GJs are eigenvectors rather of T with eigenvalues lambda j. So this is x gj j. And what I want to do is I want to show that this sum here converges to Tx as n goes to infinity. So I need to show Tyn converges to 0 as n goes to infinity. And we're going to do that in a very easy but clever way, right? So this is going to be equal to, well, yn is an Mn perp. And can remind you, well, Tm, so Tn plus 1 is T restricted to Mn perp. So it's going to be equal to Tn plus 1 yn. Second, that's fine. Yeah. So this is less than or equal to the norm of Tn plus 1, norm of yn. Well, the norm of yn is less than or equal to norm of x. This is equal to lambda n plus 1. Well, now let's use the fact that we have here that the lambdas converge to 0. So this converges to 0 as n goes to infinity. And so what have we proved? We just proved that Tx is this sum here, n equals 1 to infinity. X, gj, gj, lambda j. Okay, so in either cases, we're almost done. We've proved, we've basically diagonalized T. which is really the main the main difficulty in the proof. So in case 1, we've diagonalized t. Right? We've diagonalized t, or we show that it's diagonal with respect to this orthonormal set. So that. And case 2, we've shown, again, it's diagonal with respect to this orthonormal set. So now we're almost done. The only reason why we're not necessarily done is because we don't know if the GJs are an orthonormal basis. Okay? So we have to look at 2 kind of more cases. And these 2 cases are genuinely straightforward. So first, assume that the kernel of t is just a 0. Okay. So in this case, I claim that Gj, in either case, so I'm not going to put j equals 1 to infinity, because this could be finite. In case 1, j went from 1 to n, where tn is the, what was it? Yeah, sorry, this is an m, not an n. Right? Yeah, so we just stopped at the GJs. Basically, we stopped at m, case 1. In the second case, j went from 1 to infinity. So I'll just write it as GJ. We don't know if it's finite or countably infinite. Doesn't matter. Either way, in either case, I claim this is an orthonormal basis. Well, y is pretty straightforward. Again, just use the same trick that we've been using. We used twice already. Let's say y is going to be the sum here. X minus x gj gj. Okay. So right. So what is ty? Well, it's going to be lambda. So tg is lambda g, which is yeah. Sorry, tgjj is lambda tj. Lambda, just write it. It's been a long day. So this here, remember, as we've done these 3 or 4 times, is lambda j gj. So this is really going to be gj lambda j here. Well, this is going to be equal to 0 because tx is this sum. We proved that. Okay. So that implies that y equals 0. So that implies that x is this sum here. And that proves it. You have an orthonormal set, gj, where every x can be written as xgj, gj, that's sum. And remember, that's one of the conditions for an orthonormal basis. All right, so the other case, assume that the kernel of T is not 0. So for our purposes, that means lambda equals 0 is an eigenvalue. The obvious eigenspace is the kernel of T. Okay, so we're going to finish up by letting let's do Hj. Let's say this is an orthonormal basis for the kernel of T. So each one of these is an eigenvector of T corresponding to the eigenvalue lambda equals 0. Okay. So let's finish up by claiming that the union of these and maybe to clarify, when I say is an orthonormal basis of my original Hilbert space. Okay. So obviously, if so this shows that in the case where eventually the TMs are 0, that we actually have a finite dimensional space. Right? Yeah, so I claim this is an orthonormal basis for H. And this is not too hard. We do exactly what we had before. Again, y is x minus this sum here. This is in the kernel of T. So y is going to be, you can write it as the sum here, y, h, j, and a product h. Let's just do k. Okay, so it's a bit messy, but what is this here? This is k, or rather x, hk, hk minus, well, I'll just plug in what y is, so it's minus sum k, sum j, let's see, so it's going to be gj, hk, let's make sure we get this right, xgj, second, yeah, hk. Okay. Well, it actually doesn't matter because all of these are 0. Because these are all orthogonal. Why? T is self-adjoint. This is an eigenvector of T corresponding to lambda equals 0. This is an eigenvector of T corresponding to lambda j is not 0. Okay, and the reason why these are eigenvectors of T corresponding to lambda j not equal to 0 is because we stopped before we got any 0 eigenvalues. Now, once we hit the norm of Tm being 0, we said we're just stopping. We're not forming any new eigenvectors. So we just used eigenvectors before we have Tm being 0. So all the eigenvalues corresponding to Gj are not equal to 0. Okay, so this is going to be 0, this whole thing here for each j and each k. So this is simply going to be just this sum here. And it is a bit messy, so I'll just summarize what's going on. Well, actually, what's going on is we are genuinely finally done, at least in a self-adjoint case. Okay, so we've just proven that y, which is x minus this sum, equals this sum here. Okay, so in other words, for any arbitrary x in my Hilbert space, I wrote x as this sum here. K x, let's write this first, x hk hk plus the sum here right. So that takes care of the proof for self-adjoint T. This means that the union here is genuinely an orthonormal basis for H. Okay. All right, so let me outline the proof for normal operators. And as I said, it's basically the same proof, except some minor technical differences. Or really, you're going to use the proof for self-adjoint compact operators to get the normal operator case. Okay, so what is the outline? One, and this is really the main, it's kind of technical, so I don't really want to bother with it. It's not too hard to prove, though. You can maybe even try it yourself. You can find this online on Google. It's actually a very important result in quantum physics, what I'm going to write down. And in physics, what I'm going to write down is often called simultaneous diagonalization of observable operators. Right? So if commuting observable operators, rather. So if A and B are two operators on a separable Hilbert space, doesn't matter if they're normal or not. Let's just say they're self-adjoint and compact. Then the claim is there exists an orthonormal basis of eigenvectors let's call it, use the same notation, G, J. And the key here is that these GJs are eigenvectors for both A and B. So GJ is each GJ is an eigenvector for both A and B. So what we just proved guarantees that A has an orthonormal basis of eigenvectors. B has a possibly different orthonormal basis of eigenvectors. This lemma is saying if A and B, actually, this is going to be true if and only if A and B commute. Forgot to mention that. That's kind of the whole point. Sorry about that. So you can simultaneously diagonalize A and B. Okay. A and B have simultaneous orthonormal bases of eigenvectors if and only if AB equals BA. So again, the whole point is that in general, we know that there exists two sets of orthonormal bases of eigenvectors for A and B from what we just proved. But if A and B commute, then we can set those bases of eigenvectors to be the same. All right, and two, and this is a nice little trick you do a lot in operator theory. It's extremely elementary. So here, assume T normal. So what I'm going to do is I'm going to write, this is often called the real and imaginary part of an operator T. It's going to be T plus T star over 2, so over plus I times T minus T star over 2I. A plus I B. Okay, so you can check, I mean, there's nothing to check here, that these are compact self-adjoint, A and B. Okay, well, since T, well, so let me write it this way. You can check this. Since T star T is T, T star, A and B commute. Okay. So there exists GJ. There exists an orthonormal basis GJ of eigenvectors of both A and B, and that so that proves it. Okay. Yeah, and that's basically the idea that yeah, and because T is normal, you can check that this means that this is going to be, so since T normal, GJ will be an orthonormal basis, or rather, it's be an orthonormal basis of eigenvectors of T. Right. All right. And I mean, this is something to check, but yeah, like I said, the main point, the main technical challenge here is proving one. It's not too hard, but it's a bit of a mess. So I'm not going to really do it. All right, so finally, I'm going to talk about the Fredholm alternative in a moment.